Okay, I'm going to get back to the chapter 1 stuff. We're kind of doing a brief algebra and trig review, and I've got kind of the algebra stuff going on here first, and we'll knock some of that out, and then we'll turn our attention to trig stuff a little bit later. Of course, it's intended to be that we've all been there and done that before. So ideally, I'm not showing you nothing new, but it is good to review this and make sure that we're fine with it. All right, so we are on problem 4 in these notes here. You put some ice cubes in a glass, fill the glass with cold water, cold is important, and then let the glass sit on the table. Describe how the temperature, capital T, of the water changes as time, little t, passes. And then sketch a rough graph of the temperature of the water as a function of the elapsed time. All right, so I've got a graph set up here. I've got my time axis and then my temperature axis. Suppose here's room temperature. I've got that marked. Now, the fact that the glass is filled with cold water, you would assume that it's going to be at some temperature that is less than room temperature, right? You're going to then put ice cubes in the glass. So the temperature is going to drop as time goes on, okay, because the ice cubes are cooling it down. Now, eventually, the ice cubes will melt, okay, and the temperature of the water will approach the temperature of the room, okay. Of course, it's not going to go above room temperature, so I wouldn't want to just have this rising, above this mark here. So this would be just a quick rough sketch of, this situation going on. Now, we're going to do lots of things with rates of change in the first 4 chapters of the book. Okay, there's a lot of problems with the rates of change, and this is a good problem to just kind of think about what's changing over time. Okay, all right, let's take a look at problem 5 next. Problem 5, state the domain of each function. Write your answer using set or interval notation. Okay, part A, we've got a quadratic function. The domain of any quadratic is all real numbers. In this function here, we're asked to pick a number. It can be any number we want. Okay, whatever number that is, we're going to square it, add 5 times that number, and then subtract 1. Well, I can do that to any number I want, and I just get another number in return, right? But I can do that to any number I want. So all real numbers are going to be okay there for x. And here's my interval notation. I've got that written. Part B, g of x equal 3x divided by x squared minus 4. Okay, so we know that we can't divide by 0. Any number that would create 0 down under, we'd want to throw that away. Well, x can't be 2 or negative 2 because those two numbers are going to create 0 in the denominator. I want to make sure that I'm throwing those numbers away in the domain. Any other number is going to be fine, okay, but of course that's the only thing that I'm looking at there in that problem. Part C, h of t equal the square root of 4 minus 3t. When it comes to square roots, I don't want an overall negative to be underneath the radical. The square root of a negative is not a real number, and I only care about the real numbers that I can use here for t. So, I'm going to just do a side calculation here. I'd want 4 minus 3t, that expression underneath the radical, not to be a negative. That means that it's going to be greater than or equal to 0, okay, if I don't want that to be negative. Add 3t and then divide by 3, and you'll have t less than or equal to 4/3. Okay, so anything less than or equal to 4/3 is going to be okay. Anything bigger than 4/3, we don't want that, because then that's going to produce an overall negative number underneath the square root sign. Okay, here I'm using set builder notation. Here I'm using interval notation. Either one would be fine, if this were in class. But make sure that you're comfortable with both kinds of notation. They're going to come up all over the place for what we're doing. With set builder notation, make sure that you've got the vertical bar there. That's a necessary thing that we need when we use set builder notation. Okay, and of course with interval notation, parentheses if you're not including the number, bracket if you are including the number. Now here I'm including 4/3, right? With that being a less than or equal to, so I'm going to want to bracket by 4/3. Infinity and negative infinity are not numbers, right? So you'll never have brackets by either of those symbols. Those are just symbols to indicate unboundedness in the positive direction. Okay. Part D, k of t equals the cubed root of 4 minus 3t. Now, the fact that I've changed this to a cubed root compared to a square root totally changes everything. You see, the cubed root of a negative is a negative. Like if I were to ask you the cubed root of negative 8, that'd be negative 2, right? Because negative 2 cubed gives me negative 8. Negative 2 times negative 2 times negative 2 gives me negative 8. So unlike with a square root, with a cubed root, like we can have a negative underneath the radical. There's no problem with that. Right? All real numbers are okay to use for t. Okay, and here'd be the symbolic way to represent the set of all real numbers. We use a capital script R. A lot of books will use that. Okay, you could also use interval notation, or you could write out all real numbers. There's lots of ways to represent the fact that any number would be okay. Part E, I've got an exponential function, and f of x equal 10 to the negative x. Well, that's the same as 1 over 10 to the x. X is in the power, and no matter what x is, if I were to look at this as 1 over 10 to the x, of course, the next obvious question is can x be anything that's going to return 0 in the denominator? Well, x could be positive, negative, 0, doesn't matter. Anything with the 0 power is 1, right? If x is positive or negative, you're not going to get 0 down under, and that's the only thing that we care about. So all real numbers would be okay to use there for x. Part F, g of m equal log of m plus 5. When it comes to logarithms, we can't take log of 0, can't take log of a negative. So this m plus 5, I want that to be strictly a positive number. If you subtract 5 from both sides, anything greater than negative 5 is going to be okay to use then. Anything less than or equal to negative 5, we don't want that, because then we either have 0 or a negative overall value going into the logarithm. Okay, p of z is given there. Now, for this one, I'd want to look at a couple things. Of course, I know I can't divide by 0. So if I were to set 18 minus 6z equal to 0, you'd get z equal 3, and that's what we don't want. Okay, so 3 is going to be a problem. And underneath the radical, z plus 7 has to be non-negative. So if you say z plus 7 greater than or equal to 0, z would be greater than or equal to negative 7. So all in all, you can have any number that is negative 7 or bigger, just don't take 3 though, because we can't divide by 0. Part H, r of x is given. Okay, so of course, I know I can't divide by 0. If you were to set ln x equal to 0 and solve, you could take e of both sides. E to the ln of x is x. E to the 0 is 1. Anything to the 0 is 1. So x can't be 1 because the ln of 1 is 0. We know we can't divide by 0. Also, when it comes to logarithms, we can only have an overall positive number going into the logarithm. Okay, so I can let x be any positive number I want, just don't take x to be 1 there, because we can't divide by 0. All right, problem 6 is dealing with piecewise functions. We're going to do lots of things with piecewise functions throughout the course. So here we're just going to graph and then state the domain and the range. Now, in the part A, I've got a piecewise function with 3 different pieces, and here's the conditions on x. In a piecewise definition, there's going to be some conditions on each one of the pieces that you're going to want to be aware of, and so if you're drawing this in pencil, you'd want to erase the part that you don't want to keep on the graph. Okay. Of course, the other thing too is the fact that this is a function means that it's got to pass the vertical line test. Okay, so the end result should pass that test there. Well, let's go through the three pieces. The first one, y equal x squared, that's a parabola centered at the origin facing up. Okay, now I don't want that entire parabola to be showing because there's a condition on x. X has to be less than or equal to 1. So here I am at 1, and when I come up to that parabola, anything that is 1 or less needs to be kept. Anything that is bigger than 1, if I were to have drawn that, I would erase. Okay? And so we just have this left part on the parabola remaining. Piece 1 is now done. Piece 2, we got y equal 3, which is a horizontal line at a height of 3, if x is between 1 and 2. Okay, so I'd have that horizontal line drawn at a height of 3, but I only want to keep the piece for when I'm between 1 and 2. I would erase everywhere that is less than 1 and everywhere that is bigger than 2. Okay, and I'd have this little line segment remaining. Now, x is strictly greater than 1. That means I'm not including 1, so I'll use an open circle to represent the fact that 1, 3 would not be on the graph. X is also strictly less than 2, so I'm going to use an open circle to represent the fact that 2, 3 is also not on the graph. In general, an open circle means that the point is not on the graph, and a closed circle means that the point is on the graph. Okay. Of course, in piece 1, I've got a less than or equal to, right? So 1, 1 needs to be on the graph. I'd want a closed circle there. All right. Piece 3, we've got y equal, probably think of this as y equal negative x plus 1. That's the same thing as 1 minus x. Okay. But I would have a line, y equal negative x plus 1. That line would have a slope of negative 1 and a y-intercept at 1. Okay, so here's 0, 1. I can use that as a start point. That's my y-intercept. And then work off of the slope. The slope is negative 1. So I'll need to go up 1 and to the left 1, since that's a negative. Go up 1 and to the left 1, up 1 and the left 1. Or going up 1 to the left 1 is the same as going down 1 to the right 1. Okay, you can go down 1 to the right 1 a couple of times and gather up some points on this line flowing in the other direction. And so then we would draw on our line. Okay, now we don't want that entire line. We only want to keep the part for when x is greater than or equal to 2. So here I am at 2. When I come down to this line, anywhere that is 2 or bigger, I would keep. Anything that is less than 2, if I had drawn the rest of that line, I would need to erase. Okay. And so now my graph is complete. Notice that I do have a function. You know, I got something that's going to pass the vertical line test. If I draw a vertical line anywhere, it's going to only intersect the graph in one point. Okay, even right here at x equal 1, since 1, 1 is on the graph, 1, 3 is not on the graph. Also at x equal 2, 2, negative 1 is on the graph, 2, 3 is not on the graph, right? Okay, state the domain and the range. The domain of this function is all real numbers. There's a couple of different ways that I can get that. One option would be to look at the graph. Okay, if I scan the x-axis, if I look above or below each value and I'm on the graph, I'm in the domain. If I'm not on the graph, I'm not in the domain. Well, it's not going to matter where I'm at on the x-axis. I can be anywhere. And if I look above or below, I'm going to be on one of these three pieces here. So all real numbers are going to be represented. Now, a graph is nice, but we really didn't need a graph to get the domain. We could have very easily got that from our conditions on x, right, how this is defined. X is less than or equal to 1 in piece 1, x is between 1 and 2 in piece 2, and then x is 2 or more in piece 3. Well, if you combine all the information there about x into one statement, you're simply saying that x can be anything. And you've represented all x values in combining all three of these statements. All real numbers would be represented there. Okay, now a graph is helpful in getting the range. So to get the range, we're talking about the y values, and I can just scan the y-axis here. Looks like anywhere that is 0 or bigger, if I look to the left or to the right, I'm going to be on the graph. Also, anywhere that is negative 1 or less, if I look to the left or to the right, specifically to the right, I'm going to be on the graph. Okay. If you're on the graph, you're in the range. If you're not on the graph, you're not in the range. Well, I'm not going to be on the graph if I'm between -1 and 0, and I look to the left or to the right, because there's no graph between those two numbers there. Okay. So I'd say the set of all y such that y is greater than or equal to 0, or y is less than or equal to -1 if I'm using set notation. Okay, part B is another one, same deal. We're going to graph this function and then state the domain and the range. Here I've got two pieces. So piece 1 would be a line. Y equal x plus 2 is a line that has a slope of 1 and a y-intercept at 2. So I can start at 0, 2 on the y-axis and then use the slope. The slope is 1. So I'm going to go up 1 into the right one, up 1 to the right one, or I can go down 1 to the left one, same thing. Okay, gather up some points flowing the other direction there. And once I've got several points, I can then draw on that first line. But I don't want the entire line to be showing. I only want to keep the part for when x is less than -1. So here I am at -1. Okay, when I come up to that line, anywhere that is less than -1 I will keep. Anywhere that is -1 or bigger, if I were to have drawn all that, I would need to erase everywhere that is to the right. Okay, and of course we're strictly less than -1, so I want to make sure that I've got an open circle there at -1, 1. That point is not on the graph. Piece 1 is now done. Okay, piece 2 is also a line. Y equal -2x would be a line that has a slope of -2 and a y-intercept at 0. So here's 0, 0. I can use that as a start point and then work off of the slope. The slope is -2. So you're going to have to go up 2 and to the left 1, since that's a negative, you're going to the left. Up 2 to the left 1, up 2 to the left 1. Going up 2 into the left 1 is the same as going down 2 into the right 1, right? I could gather up some points flowing in the other direction there into quadrant 4. And once I have some points, I can then draw on this line here. Okay, now I don't want the entire line because there's a condition on x. The absolute value of x less than or equal to 1, by definition for removing the absolute value bars, would mean that x is between -1 and 1, including those numbers. So, okay, I want to keep the part of the line for which I'm between -1 and 1. Anywhere that is less than -1, if I had drawn all that, I would need to erase. Anywhere that is bigger than 1, if I were to have drawn that, I would also want to erase. You're including the endpoints with this being less than or equal to on both of those. Okay, state the domain and the range. The domain, if we scan the x-axis, it looks like anywhere that is 1 or less. If we look above or below the number there, we're going to be on the graph. Okay. And the range, if you scan the y-axis here, it looks like anywhere that is 2 or less, if you look to the left or to the right, you're going to be on the graph. Okay. Of course, make sure that you're using the variable y when you're representing range. I see sometimes students use x, and don't do that. We already know the conditions on x since we've already stated the domain. All right, we'll stop right here.